Today we will talk about the credit default swap, that is CDS. First, we will introduce some basic theoretical information about CDS, and then we will go to the Quantlib to look at CDS in Quantlib. We will introduce a class in Quantlib, that is the schedule, because it is important in CDS pricing. And later, we will talk about CDS in the Quantlib reference menu. And in the last, we will try to write a code to give us the fair spread for the CDS and also the net present value of CDS. Okay, now let's look at default risk. The default risk is the risk that the issuer of a bond or loan might not be able to meet its interest or principal payment. So here is a chart from Moody's to describe the average cumulative default rates for different rated bonds. For example, a B-rated bond might default with 5.2% possibility in year 1, but the possibility of the bond defaulting in 20 years will be as high as 54%. Like the options of stocks are used to hedge against the market risk of stocks, the credit derivatives are used to hedge against the default risks of bonds or other credit products. One of them is CDS. But for CDS, one thing that we are very concerned about is when does this company default. So let's here look at an example. If we look at the CAA rated or below bonds, the unconditional default rate of this bond to default between year 1 and year 2 is 30.5% minus 19.5%. That is around 11%. But we are not concerned about unconditional default risk. We are more concerned about the conditional default risk. The conditional default risk, also called hazard rate, is the possibility of this bond to default between year 1 and year 2. That is, the default time of this bond is after the end of year 1, but before the end of year 2. To calculate the conditional default risk, we will use the 11% divided by the possibility that it will not default in the first year. That is about 81%, 1 minus 19.5%. So that will give us about 13.7%. So why are we concerned about conditional default risk? It is because that in a credit default swap, it is like in an insurance, where the seller of the contract compensates the buyer in the event of default. Consider if you buy an insurance for your car from an insurance company. The payoff to you and to the insurance company will be very different if an accident happens tomorrow within the first year, or if an accident happens 20 years later. So the insurance company will calculate very carefully about the possibility of an accident in each year. That is also the case in the credit default swap. If the periodic payment is very high and the possibility of default is very low, the default protection buyer will not enter into this contract. And if the payment is very low while the default risk is very high, the seller will not enter into this contract. Like any other commodities or any other things that traded on market, the buyer and the seller will find a price. Okay, now let's look at an example of credit default swap. That is a 1-year CDS with payments made annually and in arrears. We assume that all the defaults always happen in the middle of a year. And if the default does happen, the accrued payments from the buyer will be made in case of default, that is also in the middle of a year. Here is a list of parameters. The hazard rate, that is usually the conditional default risk. But in this case, the conditional default risk is the same as the unconditional default risk because we have only 1 year CDS and payment is also made annually. So we have only one payment from the buyer. And there is only one period in the CDS. So the hazard rate is 3%. And the annual payment from the buyer will be 150 basis points. the recovery rate of the bond will be 50%. That is, the loss from the credit event will be 1 minus the recovery rate, that is also 50%. So the buyer will receive 50% of the notional amount from the seller, because that is the amount that is lost. And the discount rate will be 1%, and notional amount, for simplicity, we will use 1. So now let's look at the expected payment for both the buyers and the sellers. For buyers, if there is the default event, the buyer will pay half of the annual payment, because that is the accrual amount in the middle of the year. That is 75 basis points at halfway through the year. And in case of no default, the buyer will have to pay 150 basis points at the end of the year. For payments from sellers, in case of default, the seller will have to pay 1 minus recovery rate multiplied by notional amount at halfway through the year. That is 50% of the notional amount to the buyer for the loss. And in case of no default, of course, the seller will not have to pay anything. So the present value of the expected payment from the buyer will be 3% multiplied by the 75 basis points and discounted back to the beginning of time. Because the payments will be in the midpoint of the year, the discount factor will be smaller than the discount factor for the case of no default. So in case of no default, with possibility of 1 minus 3%, that is 97%, multiplied by the 150 basis points and discounted back to the beginning of time. The present value of expected payment from the seller will be 3%, that is the default risk, multiplied by 50%, that is the amount to be paid by the seller in case of default, and also discounted back to the present time. So if we use the present value of payment from the buyer to minus the present value of expected payment from the seller, we will get the net present value of the CDS for the seller. Of course, we can also get it get the net present value for the buyer if we use the payment from seller minus that from the buyer. And we can also calculate the fair spread. That is, if we assume X for the annual payment and we let the present value of expected payment from buyer to equal that of the expected payment from the seller, we can calculate X. So we can solve for X if we want the net present value of the CDS to be 0. I will leave that to yourself. You can calculate the X. It will be very simple. Now let's talk about the schedule class in Quantlib. The schedule class describes the payment schedule of credit default swap or any other derivative contracts. It has a list of arguments. The first one is effective date. That is the date when the contract becomes effective, or the beginning date of the contract. And then the termination date, that is the maturity date of the contract. The next one is period. Let's go to Quantlib website to see more details about period. Okay, first let's go to schedule and then click on period. So period has two kinds of constructors. We'll first look at the second one, that is the frequency. So if you have a payment that is scheduled once a year, you can use the frequency of annual. If you have the payment every 3 months, you will have the quarterly frequency of payment. However, if you have some very unique payment schedule, for example, if you want to make payments every 10 days, it is not listed here in this enumeration. So you will need the first constructor of period. So you can put 10 here, that is the integral, and then for time units, you can use days. So the first period can be used if your payment schedule is very uncommon and it is not listed in the frequency. Now let's go down this list. You have a calendar that is usually target. We will use target here like we did in the previous videos. And next one is business day convention. We will again go to the Quantlib website. So in schedule, we have the business day convention. The business day convention specifies the algorithm used to adjust the date in case it is not a business day. For example, if your contract matures in the 1st of March next year, for example, but if that is a Sunday, it is not a business day, usually we cannot make payments. So the business day convention will specify how you will adjust the payment day in such a case. The following business day convention will choose the first business day after the given holiday. So if your maturity date is on a Saturday and it is the 1st of March, and then you will choose the next Monday, that is the 3rd of March, as the business day. The modified following is quite similar, but it will not choose the first business day if the next business day belongs to a different month. For example, if your contract matures on the 30th of April and it is a Sunday, then if we use the following business day convention, we will choose the 1st of May, that is a Monday. But if we use modified following, the 1st of May will be in the next month, that is, it belongs to a different month. So we will choose the first business day before the holiday. So we will choose the 28th of April, that is the Friday, that is before the contract maturity date of Monday, the 30th of April. So we will have all kinds of business day conventions. You can read the descriptions by yourself. They are very easy to understand. And now let's go to the next parameter in the constructor. That is the date generation rule. For date generation rule, we will use the 20th IMM rule because this is the rule that is usually used for CDS schedules. So for exchange traded CDS, usually the effective date are taken to be the 20th of March, June, September, and December. So the termination date is also modified to be the 20th of the IMM month. The next thing in the schedule is end of month choice. So we will not choose the end of month. That is a false for the bool parameter. And then we will have a sample code here. That is how we define a schedule. So we have a CDS schedule, and we will put today, that is the effective date, maturity, that is the termination date, and F, that is a frequency that is defined earlier, and a calendar, that is the target calendar. And for business day convention and termination date convention, we will both use following. And date generation that we said earlier is the 20th IMM. And for end of month, we will choose false. There is also another way how you can specify your schedule. So in the previous way of construct a schedule, we will have to put everything in order. We will have to put today before maturity and maturity before frequency. So if you put them in the wrong orders, the constructor will not match. So the compiler will give you an error. And in make schedule, we can use this function to specify each parameter, like today, a maturity, or frequency. So if you have a frequency, you can just use with frequency and specify a frequency, like quarterly here. And all the parameters can be specified in this way, so that you don't have to remember the sequence of this constructor. Here is another example of how you can specify your schedule using make schedule function. You can try this yourself. Okay, now let's talk about CDS in Quantlib. We have a constructor of CDS that looks very complicated, but in fact very simple, much simpler than that of the option or the Black-Scholes Merton process. The first one is protection. So if let's specify which side of the protection are you in. So whether you are the seller or you are the buyer, we will use seller here. The next one is notional. The notional amount will be 1 million. The rate, that is the spread. This is the running spread that the buyer will pay for the seller. And next one is schedule. We already talked about this in the previous slide. And the business day convention. This is also about the payment convention. And we will again use the following convention. And next one is day counter. We will use the actual 360 day counter convention. The rest parameters all have their default settings, so we will use their default settings and we don't need to specify them in our code. The engine that we use for the CDS pricing is the midpoint CDS engine. It is surprising because I cannot find this engine in the Quantlib reference menu, but we can find it somewhere else. If we open the Quantlib folder and go to QL, that is the main folder for almost all the classes, and we go to pricing engines for credit products, we'll find the midpoint CDS engine. So we open this file, and at the beginning of this file, we'll find the constructors. The good thing is all the constructors in this engine can be found on the Quantlib reference menu, so we can still do our pricing. We will copy and paste it into our Word file. So the engine have 4 parameters. The first one is the default probability term structure. That is the probability of default or hazard rate in the future. So if we specify the probability of default in each of the future years, we can use it to calculate the expected rate of default and further the expected loss. And the recovery rate, that is also used in calculating the expected loss. And next one is the yield term structure of the discounter. That one we are very familiar with. And the next one is optional about the whether we want to include settlement date flows. We will ignore this one because it is optional. And we will consider each of the 3 parameters required by the engine. It will be very simple. So in next video, we will go through the coding part